Let's consider the step function v of x equals to 0 if x is less than 0, and it equals to v naught if x is greater than 0. And we're going to calculate four things. The first thing we're going to calculate is the reflection coefficient for the case that the energy is less than the potential. Then we're going to calculate the reflection coefficient if the energy is greater than the potential. And for this step function where the potential does not go to 0 to the right, here you see it stays to the right of 0, it stays v naught, it does not go back to 0. We need to show that the transmission coefficient t is not simply the amplitude of f divided by the amplitude of a. It also has this constant in front of it. So we need to show that, and then finally we have to calculate the transmission coefficient. So let's get started. As usual, we're gonna look at the solution for the Schrödinger equation for the first case. So the solution here, psi of x is equal to a e to the I k x plus b times e to the I minus I k x, and this is for x less than 0. And the solution for the Schrödinger equation where x is greater than 0 is f times e to the minus l x. This is x greater than 0. Alright, so let's plot this function here so we can get an understanding of what's going on. So this is v of x, this is x. So basically, before 0, to the left of 0, it's 0. Now let's look at the boundary condition. We only have one boundary, right, where x is equal to 0. This is our boundary. So the first boundary condition that tells us that psi is continuous over there. So we have a plus b equals to f, right? If you plug 0 here, these are just ones. The second boundary conditions tells us that the derivative is also 0, so we have I times k times a minus b must equal to minus l times f. Let's remind ourselves what's k. K, as usual, is square root of 2 times m times e divided by h bar, and L is defined as square root of 2m times v naught minus e divided by h bar. So this is for the first case where the energy, see, this is part 1, the energy is less than v naught. So the wave is coming from this side here at energy E, where E is less than v naught. This is v naught. Okay, so now if we just substitute f in equation number 2 into equation number 1, we get a plus b equals to minus I times k divided by L, right, times a minus b. Putting the a's on one side and the b's on one side, we get a times 1 plus I k divided by L. This has to be equal to minus b times 1 minus I k over L. And the reflection coefficient R is defined as B over A, right, square, which is equal to 1 plus I K over L amplitude square divided by 1 minus I K over L amplitude square, which is equal to 1 plus K over L square divided by 1 plus K over L square, which is what? It's equal to 1. Although the wave function goes into the barrier, at the end eventually it gets all reflected. This is what it means when R is equal to 1. So now let's look at B, where the energy is greater than the wave than the potential. So this is our potential, V naught. So now the wave is coming from the left at energy greater than the potential. So the solution for the Schrödinger equation reads A times e to the I k x plus B times e to the minus I k x. This is for the left region, and we have F times e to the I L x for the right region, so this is x greater than 0. So here we have k the same, and we have L is equal to square root of 2m times e minus v naught. Well, this has to be positive, right? So it has to be e minus v naught, because e is greater than v naught over h bar. Okay, so now let's look at boundary conditions for this solution. So the first boundary condition, the continuity of psi at x equals 0 gives us a plus b equals to f. Second boundary condition is the continuity of psi prime, which is I times k times a minus b is equal to I times L times f. Okay, making a substitution, we get a plus b is equal to k over L times a minus b. Putting like terms together, we get a times 1 minus k over L is equal to minus b times 1 plus k over L. Okay, so then the reflection coefficient R is equal to b over a amplitude square, which gives us 1 minus k over L square divided by 1 plus k over L square, which is the same as k minus L to the fourth, right, divided by k square minus L square parentheses square. Let's carry on. What do we know? We know that k square minus L square is the same as 2 times m divided by h bar square times e minus e plus v naught. which is the same as 2 times m times v naught divided by h bar square. We also know that k minus L is equal to the square root of 2m divided by h bar times the square root of e minus the square root of e minus v naught. So the reflection coefficient R is equal to the square root of e minus the square root of e minus v naught to the fourth divided by v naught square. See, we have to show that the transmission coefficient T is equal to the constant square root of e minus v naught divided by e times f amplitude square divided by a amplitude square. So let's draw a few things. So let's draw a box here. This is correspond to the incident wave coming at velocity v incident, v sub I, times some small time interval delta t. It's coming here, v sub I, and then it's gonna go through this barrier into the other wave, the transmitted wave, v sub t, times the time interval delta t. It's gonna carry on at velocity of t, v sub t. So from the diagram, we know that the transmission coefficient is the probability of the transmitted wave being transmitted divided by the probability of the incident wave, which is the same as f square times v sub t divided by a square times v sub I, where p of I is the probability of finding the incident particle in the box corresponding to the time interval delta t, and p of t is the probability of finding the transmitted particle in the associated box to the right of the barrier. But we know that v sub t divided by v sub I is equal to the square root of e minus v sub v naught divided by square root of e. This is from the area equation. I'm gonna put the video number and the equation number in the annotation here in this video. So we know that t is equal to the square root of e minus v naught divided by e times f over a module square t now. So for e greater than v naught, we have f plus a plus b, which is equal to a plus a times, this is, we just gonna do a substitution for b, k over L minus 1 divided by k over L plus 1. Which is equal to a times 2 times k over L divided by k over L plus 1, which is the same as 2 times k divided by k plus L times A. So this is what F equals to, right? So now finally T, transmission coefficient, is equal to F over A module square times L over K, which is the same as 2 times K divided by K plus L square times L over K. Let's just do simple algebra. So this is equal to 4 times K times L times K minus L square divided by K square minus L square square. Putting back the values for K and L, we get 4 times square root of E times square root of E minus V naught times square root of E minus square root of E minus V naught square divided by V naught square. There you have it. This is the transmission coefficient T. So now we need to, if you want to check that T plus R equals to 1, I would recommend you go ahead and do that. You will see that T plus R equals to 1.